Welcome to Rosmana Muhtar YouTube channel. Hi everyone, welcome to my YouTube channel. So what are we going to discuss for today? So our topic is de-Broglie wavelength. Okay, so we are going to discuss on how to use de-Broglie wavelength. Okay, I want to give you tips for physics STPM paper 3 in this video. So look at this question. Okay, the first tip we are going to discuss on this question. So the question is, calculate the wavelength of a 0.15 kilogram ball traveling at 0.12 meter per second. And then B, a neutron of mass 1.67 times 10 to the power of negative 27 kilogram traveling at 6.2 times 10 to the power of 4 meter per second. So what is given in the question? So we're given mass of the ball and then speed of the ball. Okay, the Broglie wavelength is given by this equation. Lambda equals to h per p. So h is the Planck constant and p is the momentum. And then how to relate with mass and velocity? So from the momentum here, p. So momentum is mass times velocity. Okay, so we substitute the mass and velocity given into the equation here. So we get the de-Broglie wavelength 3.68 times 10 to the power of negative 32 meter. Okay, so next question B, we calculate for neutron. So same equation. Okay, but this time the mass is 1.67 times 10 to the power of negative 27 kilogram for neutron, and the speed is 6.2 times 10 to the power of 4 meter per second. So the answer is 6.40 times 10 to the power of negative 12 meter. So this is for neutron. So compare these two, you can see that the wavelength for the ball, okay, with speed 0.12 meter per second is very much lower value compared to the neutron wavelength. Okay, only 6.40 times 10 to the power negative 12 meter for neutron is larger in value. So that's why when we use device like we use direction grating to find to detect the wavelength for the ball traveling at this velocity, so we cannot get because it's too much low in value. Okay, so next we try tips number 2 from this question. Okay, calculate the wavelength of an electron with a kinetic energy of 15 electron volt. So mass of electron is given as 9.11 times 10 to the power of negative 31 kilogram. Okay, so this time you are given kinetic energy 15 electron volt and the mass 9.11 times 10 to the power negative 31 kilogram. So how are we going to relate the de-Broglie wavelength here, lambda equals to h per p, with the kinetic energy? So we can relate with the p here from momentum. Okay, so momentum from the previous question is mass times velocity, and for kinetic energy is half mv squared. Okay, this is the general equation for kinetic energy. So you can see there's m and v both. So this is where we can relate momentum with the kinetic energy. So start with the kinetic energy. So we times m at the numerator and denominator of this one equation. So we get half m squared v squared per m. Okay, then mv squared, this is equals to momentum. So we substitute momentum into here. So we get kinetic energy equals to half p squared per m, and we cross multiply, we get p equals to square root of 2m k. K is kinetic energy. So now this p we substitute into here. Okay, next we substitute the values 15 electron volt, and then 15 electron volt must be convert to joule. Okay, so to convert to joule, we 15 times 1.60 times 10 to the power of negative 19. Okay, this is to convert electron volt to joule unit for energy. So this is mass of electron, and the Planck constant is 6.63 times 10 to the power of negative 34. So the answer, the wavelength is 3.17 times 10 to the power of negative 10 meter. Okay, this is the wavelength for electron. Okay, so next, tips number 3. Okay, tips number 3. We use the same thing, but this time what is given? You are given the kinetic. We are going to find the kinetic energy of the proton. So wavelength is given, and the mass of proton also given. So from the same equation just now, okay, where we derive that lambda equals to h per square root of 2 mk. So we substitute wavelength and then the mass of proton and the Planck constant. So we are going to determine the kinetic energy. Okay, so we cross multiply, we get this, and then square root both sides to get k. So we get kinetic energy is 3.29 times 10 to the power of negative 39 joule. Okay, all this is SI unit. So the kinetic energy also in SI unit joule. Okay, next, for tips number 4, we read first the question. A moving proton and a moving electron have equal wavelengths. So determine the ratio of the kinetic energy of the electron to that of a proton. So mass of electron is given and mass of proton is given. So we are going to determine the ratio of the kinetic energy. So wavelength is given. So they have equal wavelength. So let's say wavelength for electron equals to wavelength for proton. So we just write as lambda. And then the ratio of the kinetic energy. So kinetic energy of electron per kinetic energy of proton. Okay, mass of electron, mass of proton. Okay, so we form two equations for electron and for proton. Okay, so for electron, you substitute here the mass of electron. Okay, then here Ke, kinetic energy of electron, and for the proton, so you substitute mass of proton here, and this is the kinetic energy of proton. Okay, then we use simultaneous equation, so using ratio method. Okay, equation 2 divided by equation 1. So equal lambda, we can cancel this out. H also cancel out, and another one is 2. Okay, so we rearrange the equation, we get Ke per Kp. Okay, here bring up, so become Ke per Kp. Then square root both sides to eliminate the square root here. Okay, then 1.67 times 10 to the power of negative 27 divided by 9.11 times 10 to the power of negative 31. Okay, so we just rearrange the equation here, we get this. So this is the ratio of kinetic energy, electron to proton. The answer is 1833. So this is another tips for the question to find the wavelength. To use the relationship between de Broglie wavelength with the P momentum. Okay, the last one, tips number 5. Okay, what is the wavelength associated with electrons that have been accelerated through a potential difference of 28 kilovolt in a vacuum? So mass of electron is given and charge of electron is given. Okay, so we are going to determine the wavelength this time. Okay, voltage is given, mass of electron and mass of and this is the charge of electron E. Okay, continue from here. So we use principle of conservation of energy here. The kinetic energy here is the energy supplied. Okay, where the electron is has been accelerated through a potential difference to 28 kilovolt. Okay, this one is energy supplied is equals to EV is converted to kinetic energy. So we assume no loss of energy. Okay, so from here we can substitute the V here 28 kilovolt and electron charge of electron. Okay, so we substitute all these values into the equation, and then don't forget to convert 28 kilovolt into volt. So times 10 to the power of 3. Okay, here volt. So the answer is the wavelength is 7.34 times 10 to the power of negative 12 meter. Okay, so that is altogether 5 tips. The question might be asked in using the de-Broglie wavelength relationship between lambda and momentum P. Okay, got one more question here. Tips number 6. Okay, from the same just now, continue number 5, but this time we can also determine the potential difference. So how many volts of potential difference is needed to accelerate an electron in order to obtain a wavelength of 0.12 nanometer. Okay, mass of electron is given. So this time we are going to determine this V. Okay, then the lambda wavelength is given, mass of electron is given. So we just rearrange the equation here to get V. So we get V equals to h squared per 2me lambda squared. Okay, because squaring both sides, so we get this. Okay, then we substitute the values of h Planck constant, okay, 2 mass of electron, and then charge of electron, and lastly the wavelength given, nanometer, so convert to meter. Okay, so 0.12 times 10 to the power of 9 here. So there's a typing mistake here. So negative, not negative 19, but negative 9 to convert to meter. So you get the answer V equals to 104.7 volt. Okay, so that's all for the video. Okay, 6 tips on de-Broglie wavelength. Okay, how to use the de-Broglie wavelength, and thank you for watching.